Hi, in this video, I'm going to cover some of the fundamental concepts of chemical kinetics. In this particular video, I'm going to focus on developing the basic concepts, and in the next two videos, I'll focus on the mathematical derivations as well as numericals. This video is specifically designed for the F.Y.B.Sc. students of St. Xavier's College taking a course in physical chemistry. Now, first of all, what is chemical kinetics? Chemical kinetics is the study of rates of the reactions. And what do I mean by rate of a reaction? So, rate is a change in the concentration of a reactant or a product with time. Obviously, since rate of a reaction represents change in concentration divided by time, it is represented in moles per liter per second. So, if there is a reaction A giving you B, then the rate of the reaction can be expressed as negative of change in the concentration of A divided by the time in which the change took place. Also, the rate of the reaction can be represented as change in concentration of B divided by the time in which the change took place. So, delta A out here is the change in the concentration of A, whereas delta B is the change in concentration of B over the time period delta T. Now, why is there a negative sign out here? See, the negative sign is there as the concentration of A decreases with time. This delta A is a negative quantity, and this negative sign before delta A makes it overall a positive quantity. Now consider a reaction in which a reactant A gives product B. Now initially in the reaction container we'll have only molecules of A. As the time goes by, as the time progresses, there will be a few molecules of B as the reaction has started. As the time further progresses, the number of molecules of B will keep increasing. So basically, as the reaction progresses, the concentration of the reactants will decrease and the concentration of the products formed will increase. This graph depicts this situation. As you all can see, the concentration or number of molecules of A will keep decreasing with time, whereas the number of molecules of B will keep increasing with time. And when these concentrations become steady, in the sense that there is no change in the concentration of the products formed or the reactants, then we say the reaction has reached equilibrium. However, in this chapter, we are not interested in the concept of equilibrium. So this is the rate at which concentration of A decreases, and this is the rate at which the concentration of B increases. Have a look at this reaction. In this reaction, bromine is reacting with formic acid to form bromide ions, H plus ions and carbon dioxide. So basically, formaldehyde is getting converted into carbon dioxide, whereas bromine molecules are getting reduced to bromide ions. This table represents the progress of the reaction in terms of concentration of bromine. As you all can see, the concentration of bromine at 0 time is quite large. After 50 seconds, the concentration of bromine has fallen from 0.012 to 0.0101. So with progress of time, the concentration keeps decreasing. Now, the rate of reaction, as we saw in the previous slide, is defined as the change in concentration of bromine with respect to time. So if we plot a graph of bromine's concentration versus time, you will see that the concentration of bromine keeps decreasing with time. Now, the change in concentration of bromine per unit time can be represented by the slope of this graph. So, the slope of this particular graph at this point is 2.96 into 10 raised to minus 5 moles per liter per second. At this particular point, after the reaction has progressed further, the rate of the reaction is 2.09 into 10 to the power minus 5. As you all can see, from 100 seconds to 200 seconds, the rate of the reaction has decreased from 2.96 into 10 raised to minus 5 to 2.09 into 10 to the power minus 5. Obviously, as the time progresses further, the rate of the reaction is going to decrease. So at the end of 300 seconds, the slope, that is the rate of the reaction, is 1.48 into 10 to the power minus 5 moles per liter per second. However, if I had to plot a graph for formation of bromide ions or formation of carbon dioxide, then the rate of the reaction would have progressively increased till the reaction reached equilibrium. So basically, once more a reminder that slope of the graph of concentration of bromine versus time would represent the rate of the reaction at that particular time. So thus the slope of the tangent, that is the rate of the reaction, keeps decreasing as the reaction progresses. Now have a look at this reaction in which chlorobutane is converted into butanol by hydrolyzing it. Here is a table which represents the concentration levels of chlorobutane with time. As you all can again see, the concentration keeps decreasing with time, and at the end of 10,000 seconds, the concentration of chlorobutane has become 0. That means the reaction is complete at the end of 10,000 seconds. Now one can easily calculate the rate of the reaction without even plotting the graph. What we can do is calculate the difference in the concentration of chlorobutane and divide it by the corresponding time interval. So the first two readings that are presented in the table, the rate of the reaction can be written as difference between the two values, which is out here 0.100 minus 0.0905 divided by 50 seconds, which is the time interval between the two readings. Obviously, if we have to plot a graph of concentration of chlorobutane versus time, then the graph would show a decrease in the concentration of chlorobutane as time progresses, and the tangent at any point would represent the instantaneous rate of the reaction. Also, if you realize, the stoichiometric ratio of chlorobutane and butanol is 1:1, and as a consequence, the rate of fall in concentration of chlorobutane and the rate of rise in the concentration of butanol will obviously be the same, and hence the rate of fall in the concentration of chlorobutane and the rate of increase in the concentration of butanol will be the same. So whatever I said is mathematically depicted out here. Now, what if the stoichiometric ratio is not 1:1, unlike the way we saw it in the previous slide? For example, in this case, for 2 moles of A that disappear, there is only 1 mole of B that is formed. The rate of the reaction can be represented as the negative of half multiplied by the rate of change of concentration of A. However, as number of moles of B formed is only 1, the rate of the reaction will be equal to rate of formation of B. So if you have a reaction which has balancing coefficients small a, small b, c and d, then the rate of the reaction in terms of concentration of A can be represented as minus 1 upon A into change in concentration of A with respect to time, or minus 1 upon B into change in concentration of B divided by time, or 1 upon C into change in concentration of C divided by time, or 1 upon D multiplied by the rate of change of concentration of D. Obviously, the negative signs, as I told you all earlier out here, is only applied for reactants, and this is because the concentration of A as well as B will decrease with time, and hence delta A as well as delta B are negative quantities, and the negative sign in front of each of them will ensure that the overall term becomes positive and the rate of the reaction hence is positive. We got to understand what is a rate law or a rate law expression or a rate law equation. A rate law expression relates rate of a reaction with the concentration of the reactant raised to some powers. For example, for this particular reaction, the rate law expression can be written as rate equal to a constant of proportionality called rate constant into concentration of A raised to X multiplied by concentration of B raised to Y, where what is X and what is Y. So X is said to be the order of the reaction with respect to A, whereas Y is said to be the order of the reaction with respect to B. As I said earlier, K is called the rate constant of the reaction. It is also called the specific reaction rate. Also, it may be noted that these two powers need not be equal to A and B. So X need not be equal to small a and Y did not be equal to small b. Also, these two quantities X and Y are experimentally determined and they can even be 0 or a negative number. Now, have a proper look at this table. There was a reaction carried out between ammonium ions and nitrite ions. The product formed is nitrogen gas and water. This reaction was carried out multiple times with different concentrations of ammonium ions and nitrite ions. And the initial rate of the reaction was calculated and is noted down in this particular column. So, for example, when the initial concentration of ammonium ion was 0.01 and the initial concentration of nitrite ion was 0.2, the rate of the reaction was 5.4 into 10 to the power minus 7. Similarly, when the initial concentration for ammonium was 0.02 and the initial concentration of nitrite ions was 0.2, the rate of the reaction was found to be 10.8 into 10 to the power minus 7. Now, if you look at this data properly, you'll realize that from experiment 1 to experiment number 2, the concentration of nitrite ions is kept the same, but the concentration of ammonium ions is doubled. Now, what is the effect of this doubling of concentration on the rate of the reaction? So if you look at the rate of the reaction, you will realize that the rate of the reaction has doubled from 5.4 into 10 to the power minus 7 to 10.8 into 10 to the power minus 7. This clearly indicates that when we double the concentration of ammonium ions, the rate of the reaction also doubled. This indicates that the order of the reaction with respect to ammonium ions is 1. Now, if you look at experiment number 5 and experiment number 6, the initial concentration of ammonium is kept the same this time, but the concentration of nitrite ions is doubled. And what do you see out here? The rate of the reaction has also doubled from 10.8 into 10 to the power minus 7 to 21.6 into 10 to the power minus 7. This again indicates that the order of the reaction with respect to nitrite ions is also 1. And hence, the overall order of the reaction will obviously be 1 plus 1, which is equal to 2. So, rate of the reaction is directly proportional to the concentration of ammonium ions, also directly proportional to concentration of nitrite ions raised to 1, and hence overall rate of the reaction is proportional to the product of the concentration of ammonium ions and nitrate ions, and the constant of proportionality is the rate constant or the specific reaction rate. So once more a reminder, a rate law equation shows the relationship between the reaction rate and the concentration of the reactants, and if some of the reactants are in gas phase, then it would represent the pressure of the gas instead of the concentration. This rate constant K out here has a specific value for each reaction, and it is also temperature dependent. As temperature changes, the value of K for a given reaction also keeps changing. So basically, K is a characteristic of a given reaction at a given temperature. As I told you all, the order of a reaction is determined experimentally. So therefore, rate law expression also has to be determined experimentally. And as I said earlier, the rate law expression relates only the concentration of the reactants with the rate of the reaction and not the concentration of the products. Also, I told you all earlier that the order of a reaction need not be related to the stoichiometric coefficient of the reaction in the balanced chemical equation. For example, have a look at this reaction. The rate of the reaction is experimentally found to be the rate constant multiplied by the concentration of fluorine multiplied by the concentration of ClO2. So although the balancing coefficient out here before ClO2 is 2, the value of ClO2 is raised to 1. Now, what is a first order reaction? So, a first order reaction is a reaction in which the rate of the reaction is directly proportional to concentration of only one reactant raised to power 1. The rate constant therefore can be written as rate of the reaction divided by the concentration of the reactant. Now, as we learnt earlier, the rate of the reaction is represented by the unit moles per liter per second, whereas concentration of A will be represented only as moles per liter, and hence we can cancel out moles per liter, and what will be left with is second inverse or per second. So the unit of rate constant in such a case is second inverse. Now, if A is a concentration of reactant A at any point of time, whereas A0 is a concentration at 0 time, that is initially, then the relation between A and A0 is represented by this formula. I'll derive this equation in my next video. So ln A is equal to ln A0 minus K times T. And hence, if you plot a graph of ln A versus time, the graph will have a negative slope. The value of slope obviously will be the negative of the rate constant, and the y-intercept will be ln A0. A typical example of a first order reaction is out here. 2 N2O5 molecules reacting to form 4NO2 plus O2, and hence the graph for log of concentration of N2O5 versus time is aligned with a negative slope. Obviously, from this slope we can determine the value of K. As we saw that value of slope is negative of K, and therefore K will be equal to the negative of the slope. Now, what is half-life time of a reaction? So the half-life time of a reaction is the time required for the concentration of a reactant to decrease to half its initial concentration. That means if the initial concentration is A0, then at half lifetime the concentration will be A0 divided by 2. That is, when T is equal to T half, the concentration at that instant of time is half the initial concentration. Now, I'll derive this mathematically later, that half-life of a first order reaction can be represented as 0.693 divided by the rate constant. That means it doesn't involve any concentration terms, and hence T half of a first order reaction is independent of the concentration of any of the reactants. So if I want to determine half-life of N2O5 during its decomposition reaction, and if I know that the rate constant is 5.7 into 10 to the power minus 4 second inverse, then I can just plug it into this formula. So T half will be equal to 0.693 divided by 5.7 into 10 to the power minus 4, and hence, and the answer as we can see is turning out to be 1200 seconds, which is about 20 minutes. So whatever is the initial concentration of N2O5, however small or however big it is, it will take, come what may, 20 minutes to become half its original value. So this is depicted graphically as follows. Here is the concentration of the reactant A. It decreases with time, and the initial concentration out here is A0. Now, in one half-life, the concentration becomes A0 by 2. Whereas, at the end of the second half-life, the concentration becomes half of A0 by 2, which is technically 1/4 of the original concentration. So it will be A0 by 4. Similarly, at the end of 3 half-lives, the concentration will be half of A0 by 4, which is A0 by 8. That means 1/8 of the initial concentration. But I hope you all realize that the T half of a first order reaction is a constant quantity and it does not depend on the concentration of the reactants at all. So for a first order reaction, which is of the form A giving you products, we can say that when one half-life has gone past, the concentration would be half the original value, that is A0 by n, where n is 2. At the end of 2 half-lives, the concentration of the reactant will be A0 by 4, and at the end of 3 half-lives, the concentration of A will be 1/8 the initial concentration of A. Now, what is a zero order reaction? You'll be surprised to know that there are certain reactions where the rate of the reaction does not depend on the concentration of the reactants at all. The rate of the reaction hence is a constant and does not change with time. So if we consider reaction A giving you products, then a zero order reaction rate law expression will be rate equal to K into A raised to 0. Since A raised to 0 is 1, we can represent it as K. So rate of the reaction is equal to a constant quantity and does not change with the concentration of the reactant. That means if we take a large concentration or a small concentration of the reactants, the rate of the reaction will remain the same independent of the concentration of the reactant. Now, to determine the unit of K, we can rearrange this expression to write it as follows. Obviously, since A raised to 0 is 1, K is equal to rate of the reaction, and since the unit of rate of the reaction is moles per liter per second, the unit of K will also be moles per liter per second. Have a look at this graph. This is a graph of the concentration of reactant A versus time. As you all can see, the concentration of A decreases with time linearly. However, the rate of the reaction remains constant. Now for a second order reaction, the rate law expression can be written as K into A square. Obviously, I have assumed that there is only one reactant giving you a product. There can be even two reactants giving a product. In that case, suppose the reaction was A plus B giving products, then the rate of the reaction could have been written as rate equal to K multiplied by concentration of A raised to 1 into concentration of B raised to 1. The overall order of the reaction still being 2, which is 1 plus 1 coming from A as well as B. The rate constant in such a case can also be written as rate divided by the concentration of the reactant square, and since rate of the reaction is represented in moles per liter per second, and since concentration is represented in moles per liter square, one of the moles per liter will cancel out, and as a consequence the unit will be liters per moles per second or dm cube per moles per second. So one of the moles per second, as I told you all, will cancel out and we are left with 1 upon moles per liter per second or liters per mole per second. Now in such a case where there is only one reactant or the initial concentration of both the reactants is the same, the rate law expression can be modified as shown, where A is the concentration of A at any instance of time and A0 is the concentration at 0 time. Now when T is equal to T half, A will be equal to A0 by 2, and hence if it is substituted in this particular expression, we will get T half to be 1 upon K into A0. That means here the half-life depends on the initial concentration of A. If the initial concentration of A is large, then the half-life will be small. Whereas if the initial concentration of A is less, then half-life will be longer. This is a graph of 1 upon A versus time. Obviously, as we can see from this particular expression, the graph will be a straight line having y-intercept 1 upon A0 and the slope being the value of K. So here the slope is positive and its value is equal to the rate constant. So we'll summarize. If a reaction is a zero order reaction, then the rate law expression can be written as rate is equal to constant, and the integrated form of rate law expression can be written as seen out here. T half in such a case is A0 by 2K. That means the half-life is directly dependent or directly proportional to the initial concentration of the reactants. Now, if the reaction is a first order reaction, then the rate law expression can be written as R is equal to K into A raised to 1. The integrated rate law equation will be in this form. ln A is equal to ln A0 minus KT, and the half-life, as I told you all earlier, is independent of the initial concentration of the reactants. Now, what if the order of the reaction is 2? Then the rate law expression can be written as K into A square, and the integrated rate law expression, which I will derive later, is expressed as follows. And the half-life of the reaction, as we saw, is inversely proportional to the initial concentration of A. Now have a look at this reaction. Reactant A and B are forming products C and D. However, in between they have formed a transition state or an intermediate out here. The intermediate can be written as AB star or AB hash. If this reaction is exothermic, then the energy profile diagram can be drawn as shown out here. As you all can see, the reactants have more energy as compared to products. As a consequence, the energy will be released during the reaction. Now, what do we see out here? This is the energy of activation of the reaction, and only if A and B achieve this particular energy, then they can be converted into products. So, energy of activation is defined as the minimum energy that the reactant should gain in order to get converted into products. Now, if we look at this graph, this is for an endothermic reaction. So, if we assume that this particular reaction is endothermic, then the reactants have lesser energy than the products, and hence overall in the reaction energy was absorbed, and the energy of activation of the reaction can be represented as the energy gap between the reactants and the transition state formed out here. So basically, energy of activation is the minimum amount of energy required to initiate a chemical reaction, and a reaction will be exothermic if the products have less energy as compared to reactants, and it will be endothermic if the products have more energy as compared to the reactants. Now, is the rate of a reaction dependent on temperature? The answer is yes. You all have studied in lower classes that the rate of a reaction increases with increase in temperature. And why does the rate of a reaction increase with increase in temperature? So if we look at it purely from mathematical point of view, then we can say that as temperature increases, the rate constant of the reaction increases. And if the rate constant of the reaction increases, then obviously the rate of the reaction is going to increase. Whereas from molecular point of view, we can say that at higher temperatures, there is more collision between the molecules of the reactants, and as a consequence, more of the reactant molecules will be converted into products. So have a look at this graph. This is a graph of rate constant versus temperature, and as you all can see, the rate constant increases with increase in temperature exponentially. So this is the mathematical expression which relates rate constant with temperature, and it was derived by Arrhenius. And as this equation was proposed by Arrhenius, it is called Arrhenius equation. So what is K out here? The rate constant. T is obviously the temperature, the absolute temperature. EA is the energy of activation of the reaction. R is the gas constant, and A is a constant of proportionality. Now, if we convert this equation from its exponential form to logarithmic form, then we can write it as ln K is equal to minus EA upon RT plus ln A. Now, if we plot a graph of ln K versus 1 upon temperature, it will be a graph with a negative slope and a y-intercept equal to ln A. And the slope will be minus EA upon R. And since we know the value of R, we can easily calculate the energy of activation. So as I told you all, look at this graph. Graph has a negative slope, and the slope value is equal to minus EA upon R, and the y-intercept will be ln A. Now another way of looking at why rate of a reaction increases with increase in temperature is that at higher temperatures, more molecules will possess the energy of activation. So have a look at this graph. This graph is for the kinetic energy of the reactant molecules at a lower temperature, whereas the red graph is for the kinetic energy of the molecules at the higher temperature. Now suppose this value is the energy of activation of the reaction. Then as you all can see, very few molecules will have energy equivalent to energy of activation at lower temperatures. However, at higher temperatures, the entire shaded region will represent the number of molecules having energy greater than energy of activation, and therefore more molecules are capable of undergoing reaction. As the temperature increases, the curve flattens and broadens, but along with that, we have more molecules having energy greater than energy of activation. As a result, we can conclude that the reaction rates increase with increase in temperature, because at higher temperatures, more molecules will possess energy of activation. Let us once more revisit the Arrhenius equation. Constant A is a constant of proportionality and it is called the frequency factor. Now, what does this frequency factor represent? It represents the likelihood that collisions would occur with proper orientation for the reaction. So it is as good as a probability factor which takes into account the right kind of collisions that are absolutely necessary for the formation of products or for converting reactants into products. There's a graph which I showed you all earlier, and as I said, energy of activation can be calculated from the slope of the graph.